This program is a presentation of UCTV for educational and non-commercial use only.
Welcome to joining us this morning. I'm glad you got here on time to get in. There's a big crowd again that didn't make it in, so hope we don't disappoint you. First thing I want to do is introduce myself. I'm Ed Moses. I'm the director of the National Ignition Facility at Lawrence Livermore National Laboratory. You know, my friend here, Sylvia Moses, is going to introduce herself. But she told me that since she's going to tell you where she went to school, I'm supposed to tell you where I went to school. So I went to Eastchester High School back east, and then I went to Cornell University.
Okay, so my name is Sylvia Moses. I'm a 7th and 8th grade science teacher in San Francisco. I am a graduate of Granada, woo, go Matadors, and I also graduated from Berkeley with degrees in biology and earth and planetary science.
And first I want to thank Dick Farnsworth. Could you stand up, Dick? Dick is responsible for Science on Saturday, so everything we do here is his responsibility. So thank him very much. I also want to thank the Bankhead Theater staff who got us in here very safely and expeditiously. Thank you to them. You know, I always want to talk about the free lunch band. Weren't they great? You know, so they were here. And also the people at the lab who put this together, including the artists, the scientists, the engineers who made this possible. So thank you very much to them. Okay, so we're going to be talking to you about sort of what I think most people think is a very important issue, energy on our planet.
But before we start, we need our safety minute.
Yeah, so let's, you know, what's the first thing we want to make sure? Everyone in this room, so I don't have to come out into the audience and take it from them physically, turn off your phones. Pagers, come on. I know they're in there and I know they're on, right? If you want to put them on vibrate and then sit there when they're vibrating and don't get up, that's fine with me too. Okay, then anyone have a laser pointer? Put it deep in your pocket. And thirdly, and I think we have an example today in Chile, you know, if there were an earthquake or something like that, or a fire, you know, even though I think it's very unlikely these will happen, we will exit through these doors here or in the back in a very orderly manner, and we'll pay attention to our hosts and hostesses to make sure we get out and onto the street safely and sound. Okay? So let's go on with our talk.
All right, so I think you guys understand that from the video and from the news every day, clean energy is humankind's next really big challenge. We use energy every day for nearly everything we do, and we have to have some way to generate the huge amounts that we're using.
Right, and the question is, what is that energy? When you look at this map, it's kind of interesting, even though if you take away those lines that we put in as art, and you just really, this is a picture taken by satellites going over the Earth, composited, you know, a composite picture that shows where energy is being used. And I think there's some very important things to learn looking at it. First of all, you know, the United States and Europe are really covered, right? Very high density of energy. And, you know, when you look at China, India, Africa, South America, even though there's sort of a lot of light there, compared to the number of people that live there, it's really a small amount. And there's huge implications. There's another thing that's going on. It's been going on throughout history. People are moving towards big cities, right? So when you look around the world, and I'll just show you a couple examples, when we look at New York, that New York metropolitan area has around 18 million people in it. And when you look at Tokyo, which is a really interesting place, it has like around 22 million people in it. And when you look in Hong Kong, it's really similar. When you look at Beijing, there's like 27 million people in the metropolitan area. Just to get a scale of it, California's around 30 million people, right? So it's kind of an interesting thought to have in these big cities. Mexico City is like this, Sao Paulo and Rio de Janeiro in South America like this. This is the way the world's going. And how are we going to provide base power to keep everyone alive, happy, and safe, and healthy, and clean?
So before we really tackle this problem, we need to understand how much energy we use on a daily basis. So when we think about it, at every instant in time, so right now, and 2 seconds from now, we will be using 13 terawatts of power. Now, a terawatt sounds sort of scary, sounds sort of like a big number, but let's really get a grasp on how big it is. It's not a million, it's not a billion, it's 1 trillion watts. So at every instant, bam, right there, 13 terawatts of power. If we want to think about it in terms of our daily life, that would be about 670 billion of these compact fluorescent light bulbs on at one time. Or, let me get my Vanna White type, 134 billion 100-watt light bulbs going off at once.
And if we had a hair dryer,
13 billion hair dryers. That would be if every person in the entire world had 3 hair dryers going on their head at once.
or if we were really, really clean,
It would be 4 billion clothes dryers on at once all the time. And we can also think about it in terms of if you like sports cars and motorcycles. One of my favorites is 747s. It'd be equivalent to about 206,000 747s flying through the air at one time.
Well, you got to think about that. If you did that, that would be 100 million people were in the air, flying around 24 hours a day. It's quite a bit compared to what's happening. This amount of energy that we use is huge, but it's not the whole story. We'll see where that's going later. Where do we get this energy today, right? We get it from fossil fuels. Fossil fuels are carbon-based fuels. We're a carbon-based life element, and almost everything we do, whether it's coal, and we can see a coal plant burning here, this is in England, or, a petrochemical factory, this is oil and gas. That's transportation, right? Just to go over this, just to go back, that's electricity to the first order. This is transportation and electricity also. So this is what we're doing. We're burning carbon.
So where do these fossil fuels come from? Well, if we keep it real, what we need to understand is that fossil fuels is carbon. It's essentially dead life forms. So we can bring it back to the dinosaurs, we can bring it back to those ancient jungles that existed way back when. When those organisms began to die, their bodies and plants and everything sort of built up and were sort of buried underground. And so over time, that pressure built up, and with that pressure, you created coal and other natural gases.
And it took around 2 billion years for all the fossil fuels that we have today to create. And what I think is really interesting, as Sylvie said, they came in some pretty interesting forms.
So when we're talking about fossil fuels, we have sort of 3 pretty big problems that we're seeing today. First off, we're using fossil fuels way faster than they were made. So the rate at which we're using them is much, much faster than the rate at which they're even being made today. Where every year we use about 10 million years of fossil fuels.
This is kind of incredible. Remember, if you think of the life cycle, which I know you've all studied, the way life forms work is they take carbon out of the atmosphere, and make it into carbon dioxide and other building blocks of our lives, and then put it back in. It's sort of in a steady state. But now, because we're burning it so fast, we've taken that steady state out completely. And we're returning it into the atmosphere at a very high rate. And so what happens when we do that?
Well, as we saw right before the Olympics in 2008 in Beijing, there was this rapid cleanup because we're burning those fossil fuels so quickly that we're getting a bunch of pollutants in our atmosphere. So this is a picture of Beijing, I think, a few months before the Olympics, with the bird's nest. And we can see that smog, that pollution that's being released into the atmosphere as a result of the burning of fossil fuels.
I know, I was there, and this is a picture that I share. That's the short-term effects, but there's long-term effects also.
What we hear about in the news every day is that fossil fuels are affecting the climate. When we burn them, they're releasing an incredible amount of greenhouse gases. And that carbon that was inside the Earth is now being sort of released into the atmosphere, which is causing some part of global warming.
Right, so when you think about these greenhouse gases going into the atmosphere, you can think about it as putting like a blanket over the Earth, right? So energy still comes in, and it's created, but when it tries to get away from the Earth, it sort of gets trapped. And it gets trapped in the atmosphere, and it looks to most scientists, and I say the very large preponderance of scientists, that the Earth's climate is being modified by what we're doing every day, by burning carbon fuels. Now, this is kind of an interesting story because it didn't start yesterday or 10 years ago or 20 years ago. But it didn't start 1,000 years ago either. It sort of really kicked off in the 1850s, the 1800s, with the Industrial Revolution. So I wanted to go through how did energy use evolve over the last 150 years. And I think there's a lot of lessons to learn in watching how it evolved and what we're going to have to do in the future. First of all, in 1850, we were 90% a wood society. So people, all over the world were to first order cutting down forests. And then actually by, the American Revolution, and if you read Benjamin Franklin, he talks about this, that all the native forests were pretty much gone by that time. What happened next? Next thing, we went to coal. Coal was pretty much where we headed, and you could see until 1890 we were pretty much exclusively a wood and coal society. But then things changed again with the discovery of using hydroelectric. Not much of our world is hydroelectric, a few percent, but we did this. And then we went on to oil. You can see again we're pretty much a carbon society. And then when we added gas, this kept us a carbon society. You can see, even in 1960, we're essentially 100% a carbon-based society. And then finally, recently, and that's in the last 40 years, we added nuclear, and now we're a few percent nuclear in the world. And there's the most amazing part, renewables. Now, people talk about renewables as our future, but right now it's about less than 1%. That's kind of an important and sobering thing to think about. So when we look at the world right now, it's 90% carbon-based, right? What are we going to do? It's going to happen slowly, whatever we're going to do. 50 years to get out of wood, 50 years to start transitioning to oil, 50 years to start transitioning to gas. This is a hard problem for society.
So when we're looking at clean energy, which is humankind's sort of greatest challenge right now, we are seeing a big problem because when we, here, I can put the graph. Because when we look at our current energy use and then we look at our population increase, we see that by 2050 we're going to need an incredible amount of energy, far more than we're using today. So think back to that 13 terawatts. How much is that going to be increased by 2050?
It's about a factor of 3. So so we had the 3 hair dryers for every single person in the room. The population will go up, and then now they'll be using 5 hair dryers for every person in the room.
It's sort of a big problem. When we look at the potential non-carbon energy sources that we talk about when we're talking about renewable energy, we're talking about hydro, geothermal, solar thermal, solar panels like photovoltaic cells, wind, and nuclear energy.
So when you look at each one of these, what do you think about them? Let's just go through them in detail.
So when we look at hydro energy, essentially what we're doing is we're building dams in our current rivers. When the water sort of falls down through the dam, it runs a turbine, and we get energy from that. When we have geothermal energy, we're using our natural resources. Like if you've ever been to Old Faithful in Yellowstone, it's a natural geyser. And so it's run by the Earth's sort of inner heat. And so when we talk about using geothermal, we're talking about harnessing that Earth inner heat.
There's other ways we could do this. When we talked about it, solar, one way, here's a big solar farm in New Mexico. And what we have here is all these mirrors focusing on this tower that collects the light from the mirrors from the sun and heats up some salt, believe it or not. It's hot enough to turn turbines and make electricity. And I think this is kind of an interesting picture because it's a big field and you don't get very much out of it. Likewise, these photovoltaics that Sylvie talked about, even though you can sort of power your house on them, if you have other forms of electricity, they don't work very well at night. They don't work so well in the winter. They don't work well on cloudy days. Sort of a problem. In fact, when you look at all of these classic renewables, whether they're hydro or solar or wind, you sort of have problems in thinking about doing them. Again, if they went up a factor of 10 from where they are today, which is a lot of growth, we'd have 10%. And we still have the storage problems. Wind, we have wind right here. The amount of wind we have in the Altamont Pass, which is a very big place, provides enough electricity for Livermore during the afternoon. But generally, it's not on in the morning, right? Because the way the weather patterns are. And there's a lot of times of the day where we can't use it. What about nuclear? Nuclear is sort of a great idea. It uses the power of the uranium atom, and you can get a huge amount of energy out of it, and it stays on all the time. It has one problem, and the problem is it's pretty expensive. Now, other people have other problems, issues with respect to other aspects of it, but generally what keeps it out of the marketplace right now is cost. So the question we have that we're going to talk about is how do we break this dependence on coal-based energy, in a dramatic way? Is there a way to do that?
So sometimes in science, when you have a big problem like this, you need to take a step back and sort of look in the most obvious places. And one thing, when we look at our universe, when we look at even the systems on our Earth, is that it's nearly all run by star power. Stars are continuously keeping the universe going, and most of the systems on Earth, the natural systems, are dependent on energy from the sun.
So when we say, is there another idea, sometimes the answer is right in front of you. I love this picture because what do you see going past the sun? This is a real photograph. Does everyone recognize that? That's the space station, right? That's the U.S. space station. You can see, guess what are those big flat panels you see? Solar photovoltaic panels. Those are really fancy panels. They cost a lot of money and they're very efficient. But anyway, so Sylvie, why don't you tell us how it goes, how the sun works?
All right, so the sun uses fusion energy. Essentially what's going on is you have hydrogen nuclei slamming into each other in the middle of the sun. When they slam into each other, they
Fuse.
they fuse and they release a huge amount of energy. So what we can see in this video is we can see these nuclei randomly moving around, slamming into each other. And when you see them slam in, they release that big burst was energy.
Yeah, and who told us about this?
Well, our friend Albert did.
No, he actually had a tattoo on his forehead. That's how he discovered that famous equation. He was looking in the mirror one morning. Okay, so what's important about this equation? what does it say? It says E, that stands for energy, right? Mass, the M stands for mass. You know, mass is stuff, right? All this stuff is mass. We're made out of mass. Everything is mass. And then he has that famous C. C is the speed of light. They don't call it V. They don't call it L. They call it C. And you know, C is a very large number. And if you multiply C by itself, it's called C squared. And this is the important thing. A tiny amount of mass can be a huge amount of energy, right? That's what we like about that whole idea. Einstein told us how to do it, and then we have to figure out, you know, what it is we should do to make this real.
So could we essentially bring star power to Earth? Could we build a miniature sun on Earth?
Yeah, this has been the question of the ages, right? Is there a way not to collect light that comes from the sun on the Earth, but build a tiny sun on the Earth? And when we talk about tiny, we're talking about real tiny. Right now, our sun is about 1 million times the volume of the Earth, but it's also 100 million miles away. So we don't mind it being there. If it were any closer, it would be a bad day, right? So could we be like Venus or something, which is hot, and we wouldn't be having this conversation. Okay, so let's talk about what's great about fusion. And I think this is a very important picture. You know, fusion energy is extremely dense. So if you look at a 1,000 megawatt power plant, that's the amount of energy that would drive San Francisco. You would need 21,000 carloads, railroad cars of coal every year in order to do that. And remember, we talked about how much carbon would go out into the atmosphere to do it. Or we could have 10 super tankers of oil. Not only would there be a lot of carbon, but it's super expensive. What other things could we do?
So if we had a fission power plant, which is just known as a nuclear power plant, we would need 30 tons of uranium oxide. Now, if we think about it in terms of fusion, though, if we had a fusion power plant, we would need about 0.6 tons of heavy water, which, 0.6 tons is about the amount of water in a hot tub.
Right, so think about that. You can have 21,000 railroad cars of coal or a hot tub of water. Which would you rather have? You know, one is full of carbon, and one is kind of messy to drag out of the ground, and when you do it, it's really messy what goes in the air. One is water. You know, I think the answer is kind of obvious. Well, why don't we do it? It's obviously not easy.
There's been a lot of thought about how you can actually make this fusion power on Earth. And little did we know, or maybe we all know, that in our very own backyard, we actually have the world's largest laser. And we're trying to build this very tiny star using lasers.
So when Sylvie talks about tiny, you know, she talks about the diameter of your hair. Why do we want it so small? Because it's so powerful, right, that we can manage this amount of energy safely and right in our laboratory without causing any trouble, and then apply it to make energy on Earth. So this is a little movie we show. You know, you see those stars in the background that we talk about. Can we bring that energy to Earth? And we fly down on Earth through the clouds to the Livermore Valley, where we all live, or many of us live, and we look down and we see right here, which I think is very nice, the National Ignition Facility. Looks a little bit different than it used to, but I think what's very interesting about it, it's operational. We're not talking about something that's we're thinking about building. We're not talking about something that we've just started breaking ground on. We're not talking about something that we're just turning on. This actually operates every day. So this is the National Ignition Facility at the Lawrence Livermore National Laboratory. It's right here. It's about 3 miles from where we're sitting right now.
When we look at this building, we're thinking, okay, we got to build a tiny star in it. But it seems, you know, sort of hard. The building is actually the size of about 3 football fields. Seems like a lot, but when we put it into perspective, that's about the size of Costco.
Right, or as I like to say, if you go to IKEA, it's in the living room section, right? So I think that's a sort of an important point. I mean, it's a big facility as lasers go, but in terms of what we're used to in our normal lives, it's kind of small. And it would put out, our goal is a building this size, not the NIF, but a building this size, to put out enough energy to power a city like San Francisco, or Oakland and San Jose, or if you had 3 of them, power the whole Bay Area. That's what we're thinking about. Can we do that? So let's talk about where this all started. It isn't long ago that the laser was demonstrated. The first laser was demonstrated actually on May 16th, 1960, by Ted Maiman in Malibu, California. And I think it's really important right now that we celebrate this event, which actually had another important part. 3 days later, the idea of using lasers to make fusion was invented. So why don't we bring out the cake and get ready for our celebration? Sylvie, I thought this was a birthday party. Why do we have black candles?
Well, it seems like 50 is pretty old, huh?
So anyway, well, maybe for you it's old, but I'd like to really cheer this place up. Can we use lasers to make this a little bit more cheerful, Chris? So Chris is going to show you a very special laser. It's an ultraviolet laser. Watch what happens. They're magical. How do you think you do that? Does anyone have any ideas? So what we're doing is using lasers to turn black into multiple colors. Happy birthday to you. Happy birthday to you. Happy birthday, dear laser. Happy birthday to you. Okay, does anyone know how a laser works? We do this every year, so I don't care if you've heard it before. We're going to build a human laser, right? So I want to do something. First of all, I think that Sylvia deserves a great round of applause for what she's doing. Now, this is what I want you to do, right? That was just sort of applause going on randomly. Now I want you to all do the following. I want you to all concentrate, and just on your own, start clapping, and after a while, I'm going to say, synchronize. That's all I'm going to say, and then I want you to all clap together. So anyway, start clapping. Synchronize. Okay. How does a laser work? That's exactly how our laser work. If you were a quantum mechanic, and you were down in an atom or a molecule, they're making a lot of noise, but then they start listening to each other, trading information back and forth, and they come together, they become coherent, and they get everyone working together. So let's talk about what's happening in this room. How did you do that? Well, we can do a test, right? Why don't we just clap 2 fingers? Now synchronize. Very good. What is happening? You're hearing feedback in the room, right? So because you hear each other, you can synchronize. So a laser needs energy, it needs gain, and it needs feedback. Now I'm going to do another test that's going to really blow your minds. Let's do a laser like this. I want everyone to raise their right hand. Okay, now I want you to wave them together and try to synchronize. Now, you can't see each other, but if you could, you look very pathetic. Now, why can't you synchronize that way? Because you can't see each other. People in the front can't see the back. People in the back can't see the sides. Why don't you just look right here? Just look at this. What's your name? Wade. Can you stand up, Wade? I'm picking Wade because you can't see them, okay? Wade, turn around. Give him a big wave. Okay, now sit down. I want you all to look at Wade, even though you won't be able to see him once he sits down. And now try this. Raise your right hand. Okay, do it. Isn't that incredible? You're all perfectly synced up, right? Because now, instead of looking at your little domain of people, right, you all have your eyes here, and so the information that Wade has in his one hand is spreading out. Okay, so that's how a laser works. So I want to do one thing to just show, you know, the sound laser again. Why don't we just clap with one finger? We don't know. Because we need some feedback. So let's just do it like this. Okay. Very cool. Okay, thanks a lot. Okay, you now know more than I do about lasers, and I've been working on them for 40 years.
So I think what we're trying to say is that a laser, okay, so a laser is a unidirectional light. It's all one wavelength, right? Right? So let's do a check for understanding. We see all of these men at the Beijing opening ceremonies. They are all beating at one time. Do you think that represents a laser or a normal light bulb? A laser, you're totally right. It is a laser because they're all going at one time, all in unison. They're essentially marching together. Now, let's look at this image. This is an image of people in the street sort of walking around randomly. Does this represent a laser or a light bulb? A light bulb. Awesome job.
One more thing. We now know how laser works. You know, we want to build this miniature sun, and the way we build a miniature sun is we take, you know, a little piece of hydrogen like exists in the center of the sun and really have to squash it together and make it really hot. And we have to make it really dense, and we have to have high pressure. So we're going to bring in a laser target. And here it comes. And we're going to do some experiments. Do we have our kids ready yet? Okay, so where's the ball? Okay, so the first thing is, you know, we don't want to have this fly away. The first thing is, you know, can you imagine that we have to make this ball this big? That's what we have to do to make it become like a sun. And of course, what happens if we try to push this together, and we're bringing in our little laser beams. Okay, they're going to do it. Everyone get around here, all around. So what we're going to ask them to do, just to push, and don't push very hard right now. We just want to push on it and see if we can make it, really, we want to make it this big. Do you think they can do that? Why not? Just, okay, push slightly. Let's see what happens. So what's going on? It's coming at around, right? If we push it, it pushes out. Push it in with a little bit with your legs, so try to get it around her, right? And come on, push harder. Let's go. You don't look like you're pushing.
All right, thanks, guys.
Exactly the problem. That's exactly the problem. Let's hear it for those guys. That's the whole problem. Not only is it hard to make it small, but when you make it small, it's hard to make it round. So we have some ideas on how to do that, and we're going to show you about that. And we think that after 50 years of working on it, we're sort of within a year or so of figuring out how to do it or demonstrating it. So
what we're trying to do is we are taking 192 lasers. We are amping them up so they're super strong, and we're centering them on a very tiny target, about the size of what?
This big.
Not that whole container, just that little gold thing in the middle. It's about the size of a pill that you would take for medicine.
Right, and the thing that's really interesting about this, you know how we had, I think we had 10 little laser beams? And you could see that when they tried to push it, it sort of squashed around. We figured out if you had 192 of them, it's probably going to work. So this is what we're building. This is called the National Ignition Facility. Okay, everyone gets to put on their 3D glasses. This is much better than Avatar. Who's seen Avatar? I just want you to know, how much did you pay to see Avatar? So, you know, $10, $15, this is free. Okay. So this is the National Ignition Facility. I want to just show you what we're going to do. Hey, can we show them some pictures of what they look like? You can all wave at yourself now. Okay. Okay, back away. Let's get back to this. Okay. So this is the National Laser Facility, the National Ignition Facility, right? And here's where that target is going to be. And this is 3 football fields in size. This is where the battery pack is. And we're going to watch the laser beam come out of here and go to the target. So let's just run this. You got your 3Ds on? Here's the electricity. Right? And it's going back. Does it look 3D yet? It will. And this is the laser beams going to the target. Now let's watch it a little bit more carefully. Low energy light. We're going to now go in with a set of the laser beams. We're going to travel along with them, right? Does that look 3D yet? Okay, we're going in with those beams. So that's 8 beams. You notice the beams are square? All right. And they're about 1 foot across, so they're big square beams, and they're going through a little filter to clean them up, make them behave. This is, by the way, this happens in a millionth of a second, so this is super, super slow motion, right? Now you see not 8, but you see 48 of those beams, and now you see 96. On the other side of the building, the same thing is happening. We go into these switch yards, and these are about 10-story high building. Now does it look 3D? And now we see the beams aren't timed up. And now they're going to watch this. It's kind of miraculous. They time up exactly. And now we turn them blue, and we fire on that target. And that target is the size of a Tylenol pill. So it's a big building, but we squash it all into that target. And now we're building our miniature sun. And this happens in a few billionths of a second. So we make it super hot. And now we start compressing it. You watch that hydrogen compress in. And when it gets about the diameter of your hair, that's it. You know, you. Now, do you want to see what the place really looks like? You keep on your glasses. Keep on your glasses so we'll see what it really looks like. All right? This is what the laser bay really looks like. You didn't ever get a tour of it. Right? And this is what it looks like from above, right? And each one of those tubes is where one laser beam goes. And this is what the target bay looks like, where the laser beams, where the target is held, that really tiny target. It looks like a big giant V8, right? And this is the switch yard where the beams go up and down. Right, so when you look at it, this is another way of doing it.
You can take off your glasses.
You can take off your glasses. And this is just flying over the laser bay. So you just get a feeling of where the light goes. And Sylvie?
So this is images of people actually going into that big target chamber. So remember, the lasers go back and forth, get all amped up, and then they enter that big ball. So here we have some guys going in. I wish I could do that, but I think that takes like 100 hours of training or some craziness. So you go in, and there you can see them going up into the target chamber.
And the thing is that's really interesting about this is you can actually see where the target is when you get there. And that's just that little target sitting there. Now, they're not there when the target goes off because it would be an ugly day if they were. Okay? And this is how it looks like when you walk around the target chamber.
So that's the outside of that big ball.
Okay, so want to see a real shot? This is a real countdown.
2, 1, shot.
It actually makes a big bang. This is another view of it, another view of it, and then here's slow motion. Sounds like rolling thunder. And you can see the flash lamps lighting up and ready to go. Okay, so does it actually work? I just want to say this. This is a target, if that little target, which is about the size of a peppercorn, right, beforehand, and what you see that little orange splash in it, that's actually the size we've made them afterwards. And
we've shown that it actually works. We're really well underway to building that little tiny star. This is, I think, data from a shot
on December 5th.
On December 5th.
Right. And this is 100 microns across. So does everyone know what 100 microns is? Does everyone know the diameter of their hair? I'll tell you what, if you have dark, if you're a brunette, it's around 80 microns. If you're a redhead, it's around 60 microns. And if you're a blonde, it's around 50 microns. So this is sort of the diameter of your hair, right? So it's kind of an interesting place to be. And we've done this. So the next thing we have to do is put fusion fuel in it.
So we're hoping that this year will be the year, hopefully, or within the next year, that ignition or that little star is actually made within our very own facility, right out 3 miles that way.
Yeah, so the goal, the long-sought goal of achieving fusion ignition is really close. This has been a long goal, 50 years ago, but here we are. It's really exciting. In fact, achieving ignition on NIF may be a defining moment for the world's energy future. What's so good about it, right? You're burning water, the hydrogen in water, no carbon. If you look at that, laser factory, it's really, or energy factory, it looks kind of the thing you would have in cities or near cities. Doesn't have any smoke coming out of it. It's kind of almost too good to be true. But it is possible, and it is happening right now.
So we have to think about this. If now we have the technology to make this little star for a billionth of a second, we need to figure out the technology to make it real for us to build power plants that can do that, those fusion energy power plants. And what we like to call it is we call it laser inertial fusion engine, or LIFE.
Right, and LIFE is a great idea whose time is coming. And just to talk about this, how does your engine work? The way your engine works, if you look at it, is you put a little bit of gasoline in it, and you spark it, and at around 600 RPM it idles, and if you're driving along, it's probably going at a couple of thousand times a minute. And now when we talk about our facility, we want to make a fusion engine that does exactly the same thing. Except instead of making 140 horsepower or something, we want to make 1.4 million horsepower. We want to have a really kind of hot engine. And this is how it would look.
So let's look at the actual design of a LIFE power plant or a fusion power plant. What's happening is the targets, what we've been talking about, something that sort of looks like this, is being fired into the middle of this circular thing. Right when it hits the middle, all of the lasers go bam and hit that target as it's on the move. That will release an enormous amount of energy that will then...
This is what we do. When it hits, it releases the energy. We want to collect that energy, so what we have is some fluid flowing by, and you can see it, and the energy is absorbed in that fluid. And what happens now? It's kind of silly in one sense. We take that fluid, which is really hot, and we heat up some other gas, it might be even steam, and we turn a generator and we make electricity. So what happens when you plug in, your hair dryer, or if you these lights, it'll look like the kind of electricity we normally have. But when you go outside, there'll be no carbon in the atmosphere, being added to the atmosphere. There'll be no pollution. There'll be no global climate issues. There'll be no worries about, oil in the Mideast or Venezuela, because we're using water for our fuel source. How do we do this? And so we built a little model of a life power plant to see if we could. And let's see if we can get this on the camera. And this is going to be how it looks at 10 times a second. And you'll see a little target. By the way, the target is, as big as this, right? This big. I don't know if you can see it, but it's, it's about the size of a Tylenol pill, right? And we're going to be firing them at 10 times a second. Do you have it up on there, Brian? Guys?
And as you can see, there's a laser coming out. A laser coming, and it's hitting that capsule as it goes through. So this would be sort of a model of what this machine, this power plant, this fusion power plant would actually look like.
By the way, and what we're firing at it, if you could hold for a second, what we're firing at it is about the same size as a target, right? So a target, a BB gun, these kind of things are sort of similar. So these kind of technologies, as I think you all agree, are pretty commonplace. And this is the way you would do it. So why don't we fire away? And you can see the laser hitting that target. Of course, you have to do this over and over again. How much energy are you getting out of those targets?
Well, this is really, really cool. Instead of using 1,000,000 gallons of gasoline, we can use 1 liter of water. Think about a 2-liter bottle of Pepsi. That's half of that, of just plain water, in exchange for 1,000,000 gallons of gasoline.
So another way to put it, if you had a 1,000,000 horsepower gasoline engine, which you don't, but if you did, you would be going through this huge amount of gasoline per year that you could do with a quart or a liter of water. This is the excitement of fusion energy. Some people wonder whether this is practical or not. Could you make lasers that work like this? Could you make targets? Let's just talk about this. Here's a laser. Okay, so here we're burning through about a 1/2 inch of steel. That's about this big, that hole. And you can tell that that's, by the sound, zzz, that's a couple of 100 hertz, right? A couple 100 times a second. So want to see that again? So we know how to make lasers like this. Now, we wouldn't want to burn holes in things with this. We would like to hit targets. The other thing is, could you make these targets?
So we also, we can think about mass producing these targets. They would be sort of equivalent to soda cans. We know how to make soda cans. We think we know how we could make these targets really cheaply and, cost effective and efficient.
Right. So I think this is kind of an interesting point. How much do you think this soda can cost? How much do you pay for a soda? What? What's the 6-pack cost? A couple of bucks, right? So this soda can costs 1 penny to make. Think about that when you're drinking soda. And the only thing that's in it really is water. So what you're paying for is the energy to drive it here to the supermarket and then for you to pick it up. So we think we can do that. And if you look at soda cans, how many soda cans do you think are made every year? It's kind of it's an interesting number, 100 billion soda cans a year, right? So that's enough 16 soda cans for every person on Earth. So let's just go on a little bit and look at our roadmap.
So we have to think about this in terms of our lives, in terms of our children's lives, and what's the reality of it. Right now in 2010, hopefully we'll have ignition, which means we'll create that little star at the National Ignition Facility. Hopefully by 2020, we'll have a fusion power plant prototype.
Yeah, this life prototype, which isn't funded yet, so we have to be careful about it, how we talk about this, but is being discussed with utilities around the United States and with other governments around the world, could provide, the first proof that you could get energy on the grid using a life power plant or fusion energy.
Hopefully by 2030, this fusion power plant would be really commercial. It would be running our towns.
And in 2050, we would, that problem of taking carbon out of our lives? this would be a huge step forward. And if we could get, as the world in 2050, 50% of our energy decarbonized, it would be a major step with respect to global climate and pollution, geopolitics, and the like. That's what we're thinking about. These are very brave, courageous, scientific, social problems. Can we do them? We think we can. We know someone who's thought about it a lot harder than us, and that's, of course, Hollywood. The Jetsons had a fusion power plant in their backyard. And of course, Doc Brown.
You've got to come back with me. Where?
In Back to the Future. What was he running on?
Wait a minute, what are you doing, Doc?
Mr. Fusion.
I need fuel.
Now, I don't think we'll have it in our cars in the next 50 years, but we could have electrically powered cars running off fusion in that time.
So let's be real about this. Is there really fusion in our future?
Right now, when you look at this picture, where do you see your energy source from? Right? You see that tanker full of oil. What I see in the future is the following. The energy source is from the sun. It's fusion. The fuel we're using is the water. And we don't have that carbon problem in our future. We've made a huge step. Where is this going to happen? The National Ignition Facility right down the road. So if this does, we have a greater future. There's a lot of people who are are working hard on it. I want to tell you, this problem is a 50-year problem. How old are you all now on average? 15, I'd guess. This is your problem. You have to work on it together. This is what I hope to be working with you and your children on. Well, I won't be working with your children, but you will be working on in the future to make this happen. So thank you very much for your time.